Hello everyone, I am Dr. Sanjay Jain, Associate Professor in Department of Physics, IPS Academy, IES Indore. So we are going to discuss about the Hall effect and the theory of semiconductors. So let us start with the Hall effect. These are the contents. So within the time frame, if we complete these topics, it will be better. Then otherwise, I will take other lectures to complete these topics. So we start with the Hall effect. So in present scenario, in recent past, there is a lots of applications of Hall effect emerging, like switching devices, engineering and technological applications, like BLDC, brushless DC motor, and electric vehicles, used in electric vehicles. And in present scenario, it is a Hall sensor based keyboard also used. So there are so many applications we discuss later on. So let us start with our topic, Hall effect. So the Hall effect was discovered in 1879 by Edwin Hall during his doctoral degree from Hopkins University, and he measured this effect using the apparatus tour de force. But interesting thing is that it was discovered before 18 years of discovery of electrons. So the person don't know about the electrons and he discovered the Hall effect. That is the interesting fact about it. So let us start with the statement. Consider a metallic or suppose a semiconducting plate or wafer. So when current passing through this wafer of conductor or semiconductor, so let us take we pass the current according to Fleming's left hand rule. If we pass the current along the middle finger and we apply the force along this forefinger, then there will be an EMF induced along the direction of the thumb. That was observed by the Hall, and that EMF is called the Hall field, and the effect is called the Hall effect. So clearly a statement based on this we can understand using this animation picture. So let us take a metallic or semiconducting plate and we place it in a magnetic field between north and south pole of a magnet. When magnetic field lines passes through it and apply the battery on the other two sides, battery terminal plus and minus. So an EMF induced, we connect the voltmeter to other sides. So an EMF induced perpendicular to the both magnetic field, and so let us see this animation, and the electron is deflecting upward direction. It is clear shown that here electron is deflecting upward direction and deposited on the upper surface. And due to the vacancy of electron, there is a positive charge on the bottom surface. So charging process starts due to the Lorentz force acting on the electron according to the direction of the Fleming's thumb left hand rule. So let us take a slab of semiconducting or conducting material. For example, we take N-type material. Now we flow the current along the negative x-axis. Suppose current density is Jx. Let us call it as x-axis. That is y-axis, and this one is z-axis. Suppose we flow this current along this negative x-axis. So flow of current is opposite to the flow of electron, as you are aware about it. So electron will flow along the positive x-axis, and electron if we apply the magnetic field along the z direction, Bz, let us call it as a Bz, along the B direction, and consider width of this wafer is d and breadth is let us call t. As we switch on the magnetic field, the electron will deviate from its path to the upward direction according to the Fleming's left hand rule, as I talked earlier. So current flowing along this direction, magnetic field along this direction, you can, so thumb will show the direction of this induced EMF. So electron will deposited on the upper surface, and due to the vacancy of electron, unit positive charge accumulate on the bottom surface. Now this charging process starting, and it charge until the Lorentz force QVB sin theta balances the Hall force, because the charge induces on the bottom surface and the upper surface. So this positive charge will again pull the electron to downward. The situation came when both the forces are under equilibrium equal. Then charging process will stop there. So we can derive the Hall coefficient, and basis of Hall coefficient we can estimate the type of semiconductor, whether it is an N-type or P-type semiconductor, and charge carrier density, charge carrier concentration. These are the properties we can estimate from this. So next slide. So let us consider a sample of P-type semiconductor. We are taking here N-type or P-type. We can take a thickness, width. The magnetic field simultaneously exert a Lorentz force QVB sin theta, as you know that QVB sin theta. Lorentz force is always QVB sin theta. In our case, electron is flowing along the x-axis, charge on the electron is Vx, B is applied along the z direction, and theta is 90 degree. So sin 90 is 1. So Lorentz force Fl would be EVx Bz. EVx Bz. And Hall force, because it is acting along the y-axis, so Hall force Fh, Hall force would be E into Ey. That is the Hall force. Now under equilibrium condition, Hall force equal to Lorentz force. Hall force is QEY. Lorentz force, as I written here, QVx Bz. Both the forces are equal. QEY equal to QVx Bz. Then EY equal to QQ cancel out. EY equal to Vx Bz. So we calculated Hall force. Now we calculate the current density. Current density has two formulas. Jx equal to NEVD, as you know that V the drift velocity, and Jx is also current upon area. Here area is D into T. D into T. We call T into D to avoid the confusion. We write the T into D. So Vx equal to Jx upon Ne or Nq. We put this value in the equation, above equation. So we can define the Hall coefficient. Hall coefficient is defined as Hall field per unit current density per unit magnetic induction. Per unit magnetic inductions. So Hall coefficient is defined as EY upon J X B Z. If we put the value of J1, Jx1, Bzb1, then EY would be RH. The Hall coefficient is equal to the Hall fill. Now we calculated the Hall coefficient. Now we put the value of from equation 1 Jx equal to in our last slide Vx equal to Jx upon PQ. So RH comes out to be 1 upon, if we equate these two equations, I write here FL equals to FH, and if we equate these two equations, Vx Bz equal to EEY, EE cancelled out, so Bz Vx will be EY upon Bz. J equal to NeVq, so we put the value of J NeVx from here, these two equations, so we get Jx equal to Ne Ey upon Bz. Now put this value of Jx into this equation. So we get the Hall coefficient RH equal to Ey upon Ne Ey by Bz into Bz. Bz cancel out, Ey cancel out. So RH comes out to be 1 by Ne. That is the Hall coefficient we derived earlier. On that basis, we also estimated conductivity. Conductivity is also conductivity sigma. Sigma is concentration of charge carrier, and Q mobility. Sigma is mu n is the mobility. From NQ and value of Hall coefficient we can calculate Ne and put the value up here. So sigma is nothing but RH times of mobility. We get the mobility. In terms of mobility, we can write the conductivity also. Now we can conclude that if RH is positive, then the given semiconductor is p-type semiconductor. If RH is negative, then it is an n-type semiconductor. So we can calculate the concentration of charge carrier also on the base if we know the value of RH. So now our next slide depict these applications of Hall effect. So what are the main applications of Hall effect? We can determine the type of semiconductor like n-type or p-type semiconductor as I written here. If RH is positive, then it is a p-type semiconductor. If RH is negative, then it is a n-type semiconductor. Second is calculation of charge carrier concentration. We can calculate the charge concentration using this expression also. Now also we can determine the mobility of charge carrier and measurement of magnetic flux density. So it is basically used in flux meter. It can measure the unknown magnetic field. Now many applications, besides many applications, it is used in a BLDC, brushless DC motor, brushless DC motor. Like if you know it can sense the position of the magnet. So when we use a conventional DC motor, we use commutator. So in place of commutator, we can use this Hall sensor. You can see here the position of the Hall sensor. So we can see this in the diagram. Here is the commutator, and in place of commutator we use Hall sensor ICs. So it always shows the position of the north and south of the magnet. You can we have enlarged this image of commutator, and there is a 3 ICs, Hall sensor ICs there. And if north pole is coming in front of the sensor, it gives the signal to the stator winding, and stator winding again produce such current that the always north repulsion is there, and it maintain the motion. So high speed motor are used in high speed motor of like BLDC, like drone motor. It is also used. Automatic fuel level indicator. So in many vehicles, you can see that float is here in this diagram. Here is the float, and there is a small piece of magnet placed on this float, and Hall sensor is upward side. As the fuel level upright, then the distance between this Hall sensor and magnet reduces. So this gives the signal to the Hall sensor, and this digital display on this vehicle of the odometer. Next is magnetometer. Magnetometer used in your mobile phone, smartphone app. You have this shows its compass box, like app is there, and it sends the direction of the magnetic field using the Hall sensor ICs fabricated inside these mobile phones. Now we come to the next important parameter of the semiconductor is classification of semiconductors, insulators and conductors. So how we classify these materials? So these materials that can easily flow the electricity are conductors. As you know that metals, aluminum, copper, silver are the metals. And semiconducting materials, that electrical conductivity lie between these conductors and insulators. So, and the insulators are the bad conductor of electricity. So, in generally, electrical resistivity is order of 10 to the power minus 8 to 10 to the power minus 4 ohm centimeter conductors have, and resistivity of this insulator lie between this 10 to the power 8 to 10 to the power 18 ohm centimeter. So comparatively, we can see this with the diagram. Semiconductors, so electrical conductivity go toward the 10 to the power minus 10 ohm centimeter, then it is a conductor, and if it goes toward the 10 to the power 18 ohm centimeter, then it is would be insulators. So semiconductors have in between these two conductivities. On the basis of band theory of solids, we can also classify these conductors, semiconductors and insulators. Insulator has large band gap greater than 5 or 6 electron volts, and semiconductor has about 1 electron volt, and in case of metals, they are overlapping each other. So comparative studies are there. Conductivity, on the basis of conductivity, they are highly conductive. Electrons are loosely bound to atoms in conductors and can move freely anywhere. Example, already know copper, aluminum and gold. Semiconductors have moderate electrical conductivity, that is in between the conductor and insulators. Examples, silicon, germanium. Insulators have low electrical conductivity and electrons are tightly bound to atoms. do not move. So therefore the examples are glass, rubber and non-metallic. On the basis of band structure we can also classify. They have overlapping band structure. Energy valence band and conduction band are almost overlapping together. In case of semiconductor is order of 1 electron volt, and in case of insulator it is order of 6 electron volt. Yeah, on the basis of electron mobility, conductors have high mobility, freely responds to electric field, but in case of semiconductors electron mobility is intermediate, and in case of insulator electron has very low mobility. Temperature dependence, conductivity or decreases with increasing temperature, and in case of semiconductor conductivity increases as the temperature increases, and in case of insulator it increases slightly with temperature but not remains low. So there are example. Now we can derive the concentration of electrons in conduction band of a band. We use the blackboard for this. So as you know that in case of semiconductors, material have band structures. It has conduction band, valence band, conduction band has electrons, valence band has holes. In case of pure semiconductor, both numbers are equal. In case of pure semiconductor, both numbers are equal. Let us say bottom of the energy is EC, top of the valence band energy is EV, and Fermi level energy is EF. It is the reside at the center of this band. Now it is an n-type material, then number of electrons surely will be greater than the number of holes. So electron concentration in conduction band concentration in conduction band between the energy E and E plus dE can be written as dN equal to ZE, Z function of E, Fermi function E and dE. ZE is the density of states. For conduction band, we can write this equation as 4 pi upon h cube 2mn star to the power 3 by 2 and E minus EC to the power 1 by 2. And you know the Fermi function as Fermi function shows the probability of occurrence of the electron in a particular state E. So expression for this can be written as f of E equal to e to the power E minus EF by KT. E minus EF by KT. So let us call for as a approximation, if E minus EF is greater than KT, then this term will be large as compared to this term. So this one can be neglected. Now new equation would be f of E equal to 1 by e to the power e minus ef. So we can write minus e minus ef by kt. Now you can put the value of Fe and density of state. Density of state is the number of states per unit volume per unit energy interval between the E and D. So you can put the value of E, Ze and Fe into this equation. So our concentration of electron 4 pi upon h cube 2 mn star to the power 3 by 2 into E minus Ec to the power 1 by 2 into e to the power minus E minus Ef by kt. If you want to calculate this total number of electrons from Ec to infinity, then we can integrate this equation from Ec, bottom of Ec, the energy of bottom of conduction band, Ec to infinity into D. So you can solve this integral. Dn is n. Take this constant outside. 4 pi upon h cube 2 mn star. Mn star is the effective mass of electron. Mn star is the effective mass of electron. So let us take integral limit is Ac to infinity and E minus Ec E minus Ec to the power 1 by 2 e to the power minus E minus Ef by kt dE. Now we have to solve this integral. So we can rearrange this equation. Okay, let's write this here. N equal to 4 pi upon h cube 2 mn star to the power 3 by 2 Ec to infinity E minus Ec now we can add and subtract these two equation minus Ec and plus Ec. So equation won't affect it if we add and subtract these two quantity. Now we can take outside this equation Ec minus Ef 4 pi upon h cube 2 mn star to the 3 by 2 e to the power minus Ec minus Ef Ec minus Ef by kt, take outside and into integral Ec to infinity E minus Ec to the power 1 by 2 e to the power minus E minus Ec by kt dE. Now this is the symmetrical equation. We can solve this integral using a standard integral formula. So we know that the standard integral is 0 to infinity x to the power 1 by 2 e to the power minus ax dx. Value is root pi over 2a to the power 3 by 2. Let's compare this equation with x equal to, in case of our case, e minus ec, and a equals to 1 by kt. A equals to 1 by kt. We can also change the limit. As the e equal to ec, x would be 0, is the lower limit, and x equal to e equals to infinity, x would be infinity. So limit will be changed, x equal to 0 to x equal to infinity, and this equation, under this equation we can write d equal to dx. So our integral converted, and we put the value here. So n equal to 4 upon h cube 2mn star whole to the power 3 by 2, as it is there, e to the power minus ec minus ef by kt into solution of this integral is root pi upon 2 a to the power 3 by 2. So root pi upon 2 times value of a is 1 by kt. So kt to the power 3 by 2 will come in multiple. So we can rearrange this equation, and whole term can be written as 2 times of 2 pi mn star kt upon h cube upon h square to the power 3 by 2 into minus ec minus ef by kt, or we can write it as n equal to nc, namely this term is nc e to the power minus ec minus ef by kt. So this is our final expression, where nc the effective density of states in conduction band. Effective density of states in conduction band, that is the nc equal to 2 times of 2 pi mn star kt upon h square to the power 3 by 2. So that is our expression for the concentration of electrons in a conduction band. Now we come to we can also derive the concentration of holes in valence band. Concentration of holes in valence band. Concentration of holes in valence band. Concentration of holes can be calculated using the same expression, density of states, that is the dp is the concentration of holes between the energy interval E and E plus D, and density of states again in valence band, density of states in valence band multiply by 1 minus Fe, 1 minus Fe into dE, 1 minus Fe into dE. Because we have not taken here Fe, total probability, composite probability is 1 of finding the electron in either conduction band or valence band. So sum of probabilities will 1. So for to calculate the probability of occurrence of valence band, Fe is subtracted from 1 and integrated by integrating this equation. So we can take the limit, because energy of the bottom is the EV, and starting from minus infinity, so we can take minus infinity to EV. ZE, the density of states, 1 minus Fe d. Now density of states, again in case of valence band, we can write ZE equals to 4 pi upon h cube into 2 mp star. In place of mn star, we write here mp star. Mp star is the effective mass of hole into KT into E minus EV minus E to the power 1 by 2. That is the density of states in valence band. And we calculate here 1 minus Fe separately. 1 minus, you know that the value of Fe is 1 plus e to the power E minus EF upon KT. So we can solve this equation, take the LCM. By KT, and denominator will be 1 plus e to the power E minus EF by KT. Now again do some approximation, because energy of all the electrons will be below EV, below EF, so this term will be negatively infinity and tends to 0. So this term can be neglected in comparison to 1. So 1 minus value of 1 minus Fe would be e to the power E minus e to the power E minus EF by KT. Now put this value of 1 minus Fe and ZE into this equation. That would convert to, so we can write the integral minus infinity to EV 4 pi upon h cube again 2 mp star whole to the power 3 by 2 and e to the power E minus EF by KT into D. Now this is the constant term. You can take outside the integral 4 pi upon h cube 2 mp star whole to the power 3 by 2, and one missing term is there, EV minus. I have not written here. EV minus E to the power 1 by 2 e to the power E minus EF e to the power minus EF by KT D. Now I took outside this term, and integral limit is minus infinity to EV, that is EV minus E to the power 1 by 2. Rearrange this term, E. We can also write take minus outside, so we can write EF minus EC, EF minus E, and subtract the one term EV minus E. EV, it won't affect the result, divided by KT and D. So P equal to 4 pi upon H cube 2 MP star 3 by 2, and the rearrange this term, minus infinity to EV, take the outside common, EV minus E. So we take the outside as minus EF minus EV, and minus infinity to EV. EV minus E as it is there, we can write into e to the power minus EV minus E by KT into D. Again, it is a standard form of integral. So to compare this integral, let us take EV minus E equals to X and A equal to 1 by KT. So result of the integral would be P equals to 4 pi upon H cube 2 MP star to the power 3 by 2 e to the power minus EF minus EV into root pi. Result of the integral will be root pi. I am directly writing the result of the integral because process already told in earlier derivation, 2a k to the power 3 by 2. So P will be, we can rearrange this term, 2 times of 2 MP star KT upon H cube whole to the power 3 by 2 e to the power minus EF minus EV by KT. Let us recall this as, again, P will be equal to NV into e to the power minus EF minus EV by KT, where NV is the effective density of states, in valence band. So NV is replaced 2 times of 2 MP star, and it is that other thing is the temperature dependent density of states, 2 MP star KT upon H square whole to the power, sorry, I should write here H square whole to the power 3 by 2. That is NV. So that's all. We have derived these two equation for concentration of electrons and concentration of holes. So on the basis of these two equations, we can derive the Fermi energy at the center of this conduction and valence band. That we will discover on our next video. Thank you.